All right, let's do our day 3 of notes and finish up simple harmonic motion. Here's what you should have taken away from the last time we got together. The modeling equations, of course, what we're doing here is we're looking at an oscillating mass in simple harmonic motion. We've been talking about a mass on a spring oscillating vertically, and we want to model where it is at any point in time, how fast it's going, and what its acceleration is. And our first equation is the x equals x0 sine omega t. And the only difference is over here, we've put in 2 pi times the frequency for omega. Where x0 here is the maximum amplitude. So x0 is the same as a. So then we took the derivative of this function. The omega popped out front. We keep the x0 and sine turns into cosine. And we get v equals omega x0 cosine omega t. Keeping in mind that whatever is out in front is the biggest that this function can ever be, because when the cosine omega t is 1, the answer will be omega x0. Therefore, our maximum velocity will be omega x0. And in like fashion, here's our equation for acceleration. When we take the derivative of the velocity function, another omega pops out front. The derivative of cosine is negative sine, so there's your negative. The omega turns into omega squared, the x0 stays there, and we get the sine back. Everything out front is the maximum that this function can ever be. So our maximum acceleration is negative omega squared x0. All right, now to the definition of simple harmonic motion, because we have lots of things that oscillate that might not meet the definition for simple harmonic motion. You might think, why don't we start with this up front? Well, you really need to understand how acceleration and position relate to each other to know if it meets the definition. So simple harmonic motion is motion that takes place when the restoring force, you always have to have a restoring force, on the object is proportional to its displacement from the equilibrium position. That's really important. It has to be proportional to its displacement from the equilibrium position. And it has to be directed back away from the equilibrium position. So in general, the force has to be proportional to negative x, which means, given F net equals ma, that acceleration will be proportional to the negative displacement away from equilibrium. And our defining equation for simple harmonic motion for acceleration, we just went over the A equation, A equals negative omega squared x0 sine omega t, where the x0 sine omega t is just x, right? You could look back at that first equation. So here we see that our acceleration is proportional to negative x, which is our requirement right here. So this is very important. That's the defining equation for simple harmonic motion. That's simply our equation, our modeling equation from the previous page. So what does that mean the graph will look like? Well, the classic graph, the negative sign here, if we plot a versus x, hopefully this looks linear to you, right? Even though there's a squared, you're not plotting omega. We're plotting x on the x-axis, so it's going to be nice and linear. It's going to have a negative slope. And the omega squared should be the slope. So let's draw a nice trend line here. Let's do it in red. It should look something like that. So let's talk about, do these two types of oscillation meet the definition of simple harmonic motion? Well, an oscillating mass horizontally on a spring. Well, if we write down the equation that governs force and mass on a spring, that would be Hooke's law, Fs equals negative kx. Remember, the Regents reference table doesn't have the negative sign, but the AP does. That's to remind us that the force is always in the opposite direction as the stretch. This is Fs equals kx. So here we see that the force is proportional to negative displacement from the equilibrium position. So in mass oscillating on a spring, check, that is simple harmonic motion. What about a ball bouncing on the ground? So if a ball is bouncing on the ground, it's going up and down, and occasionally it's down there, and occasionally it's up here at the top. Is the restoring force proportional to the negative of the displacement? Well, when it's displaced in the positive direction, the force is in the negative direction, so that's good. But the bad part is, what is the force? Well, the force pulling it back down is the force of gravity, which is simply mg. And here we have the exact same force of gravity, Fg equals mg. And you might say, no, Mr. Poyer, little g varies with height. I know, but in a small band near the surface of the Earth, we assume little g to be a constant. So here we can see that, that it isn't proportional to negative x. We consider the force of gravity on a given mass to be a constant near the surface of the Earth. So even though the ball is bouncing up and down, it's undergoing oscillatory motion. It does not meet the requirement for simple harmonic motion because the force is not proportional to the displacement from the equilibrium position. So here we have, we just answered this question, but we'll take a look at it in a little more detail. We have a mass oscillating on a spring, and we have F net equals ma. This time we have a spring force. If we put in the spring force, it's minus kx. And then if we rearrange for a, we get acceleration is equal to negative kx over m. And there we see that the acceleration is proportional to, there's our negative, there's our x. So this is the classic case of simple harmonic motion, the mass oscillating on a spring. So what's on your reference table for simple harmonic motion? What do we need to know for the AP exam? Well, here's a little snip of what's on the reference table. There are basically three equations for simple harmonic motion. This one really, if you cross multiply, is the omega equals 2 pi f. It's nice that they get the period in there too. They make a little buffet out of it. And then we have the period of the mass on a spring. We've dealt with this one before, 2 pi squared root of m over k. And the period of the pendulum, we did a 2-day pendulum lab back in December, 2 pi squared root of L over g. So these are the two classic simple harmonic motion equations that we'll be asked to deal with. And of course, you should know the equations for displacement, velocity, and acceleration, those derivative equations. There'll be lots of questions regarding proportional reasoning with these. These are fun to do proportional reasoning with. All right, so let's determine the equations for period, frequency, and angular frequency for a mass oscillating on a spring. Why don't you take a moment to do those? Except first, I'll start you with the period one because you already know that we just did this on the previous page, right? The period of a mass oscillating on a spring, there's that famous 2 pi out front, square root of m over k. So why don't you pause the video, take a few seconds, and come up with the equations for frequency and angular frequency. All right, to get the frequency, one simply has to invert the period, right? Because frequency is 1 over the period. So what do we get when we invert the right-hand side? Well, we'll have that the frequency is equal to 1 over 2 pi, because that gets inverted. And we're inverting the square root sign, so we're going to have the square root of k over m. Sorry about my mouse work. Not very good with the mouse yet. And then angular frequency. How do we get angular frequency? Well, omega, not w, is 2 pi times whatever your frequency is. Well, here's our frequency. So if we multiply 2 pi by this, notice conveniently the 1 over 2 pi goes away. And our angular frequency will just be the square root of k over m. That would make a nice multiple choice question right there. All right, let's take a look at the energies with a mass oscillating on a spring in simple harmonic motion. And we'll have a little energy chart. This should remind you of the displacement, velocity, acceleration, and force chart that we did in video 1. So here we have the mass oscillating back and forth, and in each of the cells, we're either going to put 0, KE max, because notice we're only dealing with the extremes here, off to the right and off to the left. These are the two extreme cases, so if we were to pick some place in the middle, like here, it would have some potential energy and some kinetic energy. We're just picking the places where it's going to have all one or the other, not a blend of the two. So when we pull the mass all the way to the right, before it starts heading back to the left, what kind of energy does it have? Well, Hopefully you remember that at the extremes, if you envision a mass oscillating on a spring, at the extremes it's not moving. So there should be no kinetic energy, and it should have all potential energy, right? The spring potential energy is 1 half kx squared, US equals 1 half kx squared, which means the total energy is going to be the KE plus the US, which will be just the US because there is no KE. So the first row should look like that. Why don't you pause the video, take a minute, and fill out the remaining 6 boxes to figure out what the other energies would be. All right. As the mass passes through the equilibrium position here, where there's no stretch, um, it's going the fastest here. So you're going to have all KE, and you'll have no potential energy because there will be no stretch. You will have an X of 0, and the total energy then would equal the KE max. Now, keep in mind, due to energy conservation, these two will be the same number, right? The spring potential energy out there to the right will equal, numerically, the kinetic energy at the unstretched position. And then when the spring is coiled up and all the way to the left, we once again have spring potential energy and no kinetic energy, so it should look just like row number 1, and it does. Again, keep in mind that these values are all the same over here on the right due to energy conservation. All right, let's talk about what a graph of energy versus displacement would look like during this oscillation, where the mass oscillates between x0 and negative x0. Here's your x0 and negative x0. Now, of course, the mass is going to keep going back and forth, but the energy graphs will be a static picture. So I think the easiest one to graph first is the spring potential energy, because we know the equation for spring potential energy versus x. We have US equals 1 half kx squared. So it's a parabola. So over on this side, it's going to look like that. And over on this side, it'll look like that. So our spring potential energy is going to be a parabola on both sides. That should have been symmetric. I know I didn't draw that very well. Let's switch colors to do the KE. We'll do the KE in blue. And the kinetic energy, of course, as we talked about, is going to be 0 at the extremes. And then since the total energy doesn't change, the total energy will be a flat line across the top. The red curve and the blue curve will have to add to, I'll do it as a green curve in a moment. So this must be a parabola that's upside down, so that at any given spot, like here, if you add that number and that number, it will give you the total energy. So let's sketch in the total energy in green. The total energy graph, E total, would look like that flat line. Now let's go back to red for a moment, and we should probably finish that up. There. Not artfully drawn, but hopefully you get the idea. All right, on to our last page for simple harmonic motion. Let's work a couple of problems here, proportional reasoning problems. We're going to put a mass m on a spring, pull it back at distance a, that would be your amplitude from the equilibrium position, and let it go, and it will oscillate in simple harmonic motion. And what we're asking here is if the mass is pulled back twice as far and then released, what effect will it have on the mass's period? Well, if you remember how to do simple harmonic motion questions, the first thing you should do is write down the governing equation. The period of a mass oscillating on a spring is going to be 2 pi square root of m over k. And I don't see anything about x in here. No matter how far you pull it out, the period is not going to change. It might go faster going from position to position, but faster meaning speed, but in terms of time, it won't take any more or less time. So there should be no effect. No effect. No effect. If the mass is doubled and released, what will happen to the period and the angular frequency. Why don't you pause the video, take a moment, and think about those. All right, let's change colors as always. If the mass is doubled, what effect does it have? So as always, we put a little 2 in front of whatever is changing, and we can't ignore the square root house. So what do we have new that's in blue? The new period will be the square root of 2 bigger than it was before. What about the angular frequency? Well, on a previous page, we found the angular frequency, omega, which is 2 pi times the frequency, would be the square root of k over m. And as always, let's switch colors. And we put the number in a different color in front of what's changing. If we double the mass, how much bigger or smaller will our new answer be? Well, it will be 1 over radical 2, bigger than it was before. All right, our last simple harmonic motion page. We're being asked to determine the period, frequency, and angular frequency for a mass on a string. So we've already done it for an oscillating mass on a spring. So why don't you take a moment, pause the video, and come up with the 3 equations for period, frequency, and angular frequency. All right, we would start with the equation off the reference table for period, 2 pi, square root of L over G. That's an L. And then frequency would be the inverse of period. So we just want to invert everything. So that should be 1 over 2 pi, square root of G over L. Oh, I missed my smartboard. And the angular frequency will be 2 pi times the frequency that we just found. And by multiplying by 2 pi, that will get rid of that 1 over 2 pi. So this will be just the square root of G over L. That's an L. All right, that's the unit of simple harmonic motion. I hope you enjoyed. I hope you enjoyed the mathematical nature of it and the different look at slopes, which would be derivatives. And I think the modeling equations are fun to be able to find the position, velocity, and acceleration of a mass undergoing simple harmonic motion at any point in time.